So welcome to the seminar. And today we have Dr. Tamar Rott Shaham, is a postdoc researcher at the MIT CSL, in Professor Antonio Torabad, and she earned her PhD from the EZ faculty at Exonian, supervised by Professor Thomas Matali. So Tamar has received several awards, including the ICCV 2019 Best Paper Award, the Google WTM Scholarship, Adobe Research Fellowship, the Rothschild Postdoctoral Fellowship, the Vatal Jackerman Postdoctoral Fellowship, and the 3 postdoctoral awards. So welcome and welcome.
Great to be here. Thank you very much for having me. Just a little bit about myself. Most of it was already mentioned. I did all my academic degree at the ECU department of the Technion, and then 2.5 years ago, I moved to Boston and started my postdoc at MIT with Antonio Torabad. So let's just start. So I assume you are all convinced that deep neural networks are extremely powerful nowadays. So for example, we have networks that can generate super realistic videos just by prompting them with a textual prompt. Networks that can help us drive cars in a very safe manner, and even discover new structures of proteins. Now, what's really nice about networks nowadays, or models in general, is that we can actually interact with them in a way that is very natural and very human-like in this example.
Hey, ChatGPT, so you can talk now.
Yes, I can. What's on your mind, Alex?
That's pretty exciting. How does it feel to be able to talk instead of having to type all of the time?
It's pretty exciting to be able to have these voice-like conversations. It makes interactions feel more natural and dynamic.
So it's not a wonder that a lot of companies are now fake AI models is part of their products. So I'm sure you won't be surprised if I'll tell you that when you look for a specific movie recommendation on Netflix, or looking to find a specific product on Amazon, and even when you use Google search, you actually interact with an AI model behind the scene. But while it seems like the performance of these models are constantly increasing, there seems to be a constant gap between that and the amount of understanding we have regarding how this model actually operates from the inside. And when I ask how these models, how they operate from the inside, you can actually ask multiple questions. So for example, what is the exact knowledge that these models encode from the inside? Maybe something about what are the algorithmic operations that they implement in order to solve different tasks. Something about why sometimes failure modes are happening, and so on and so on. And as I'll show you in the talk today, the current tools that we have nowadays only enables us to answer this type of question in a very particular setting, a very particular task, and maybe very specific data. And therefore, we can only understand partial behavior of the model, but not the model as a whole. This is already true for the models we see today. What about the models that we will have in the near future? So some people predict that AI models will just continue to be even more powerful and more sophisticated, maybe will be better than us in many aspects of society in a way that might be very unpredictable. And while I'm not sure this is exactly what's going to happen, I'm sure that with the current rapid progress with AI models, we should be able to prevent them to act in an unsafe, harmful, or biased manner. And for that, it's not enough to have this only partial explanation regarding the model behavior. We need to be able to understand all possible behaviors of a model. So just a little bit about myself with all these research questions. So I did my PhD on generative models. Perhaps my most famous work is Tingan that won the in ICCP, where we show that we can actually train a generative model from just a single training example. And that sort of got a lot of attention from the computer vision community, the machine learning community, but not only from these communities, but also from other scientific communities where people use Tingan for their own field of research. And then a little bit more than 2 years ago, I moved to Boston, started my postdoc. It almost felt like a different era where we don't train our own models anymore, but we get them from an external resources. And this model seems to be so powerful. I started to be very curious regarding how these models operate, how do they achieve these like very high-end performance. So I switched from working on making models better to understand what's going on inside. I started to look for internal mechanisms that these models implement in order to solve different tasks. And I soon discovered that all the tools that we have today in order to solve these problems are kind of like not scalable. And if we want to be able to understand very large foundation models, we need to scale up the way we produce these kind of experiments. So in the second part of this talk, I'm going to talk about how we can automate the scientific procedure of trying to explain what's going on inside a neural network. And because this talk is going to include a lot of details, let me show you a quick roadmap of where I'm going to take you. So I'm going to start by talking about how we can reveal internal mechanisms inside language models that enables us to solve different tasks. And I'm going to start with a very, very simple mechanism, which is the ability of language models to just track the information that we presented. And then I'm going to make stuff a little bit more complicated. And we're going to talk about how language models not only track general information, but how they track different beliefs that humans might have. And I hope that at this point, you will be convinced that all the tools that we have today are very manual and not scalable. Then I'm going to show you our effort to scale up the way we understand neural networks with automated interpretability. And I'm also going to talk about how we can evaluate explanations that we get with our methods. Okay, so let's just start. So I want to show you our discovery regarding how language models actually track information that we present today. What do I mean by tracking information? So assuming I have my bio, and I'll show it to a language model, and then I'll ask the language model, what is my current institution? So the language model should be able to say that MIT is my current institution because it was actually presented in context. Now the question is how? How does the language model know to look back at MIT and say, this is my current institution? So to answer that question, we built this data set. It's called empathy tracking, and it has tasks that looks as follows. So we have a sequence of boxes presented in text. Each box has labels, and then inside each box we have a different object. And then we ask the language model what is inside a specific box. So in this example, we ask what is inside box G. And the language model should be able to say that box G contains the pattern because that was actually presented in code. Now the question is how? So let's do a quick recap regarding how language models actually process text. So when we show a specific prompt to the language model, it first goes to a tokenization process. And each word is going to represent us by a discrete value. And then each of these values is going to be processed to a sequence of layers. Each layer contains multiple units. And all these units contribute together to the prediction of the final word, which is after in this case. And this is also why some people call them this network a neural network, because you can think about each unit here as a neuron in the network that contributes some attribution value to the total computation of the prediction. So the first question I want to tackle is what part of the language model is actually participating in doing entity tracking? And for that, we're going to use a technique called fetching, and it goes as follows. When we have another entity tracking task with a different correct answer, we will feed it to our language model and collect all the internal representations that give us the prediction of the word count. And now the assumption is that if a specific unit inside our model is contributing to the entity tracking task, is actually part of producing the final result, then if we will copy paste its state from the second sentence to the first sentence, and then recalculate the prediction of the model, then the prediction should be affected in a way that it will flip from apple, the correct answer of the first sentence, to cup, the correct answer of the second. And we can do this procedure again and again for all the units in our model and see what are the units that actually contribute to the prediction in a way that flips the prediction from apple to cup. Okay, so we found this subnetwork inside our model, the units that actually contribute to calculating the final information we care about. And we found something very interesting about this subnetwork. So it contains only 75 attention heads, which are very small portion of the full model size. And actually, with only these 75 attention heads, zeroing out all the rest of the attention heads, we can actually recover the full performance of the full model on this task of entity tracking. And now I want to show you that we can do even more, not only locate where entity tracking is happening, but also finding the functionality that each of these units actually encode in order to solve entity tracking. Let me show you how we do that. But before, just a quick hint. Actually, the value of the correct answer, apple, is never been translated through this subnetwork, but some other sort of information that lets the model know that apple is the correct answer. And let me show you how we found that. Okay, so assuming I want now to analyze what is the exact functionality of a specific unit in my subnetwork, this unit is in layer 15. It actually processes the token G, okay, the label of the box we query. So the first hypothesis we had was that that unit actually encodes the information regarding the correct answer already. So it basically encodes the value of the word up. If that is the case, then I can design another input sentence where apple is not presented and ask about another box. And then if I copy paste the state of that unit from the first sentence to the second sentence, then the prediction will flip from left to apple. Right? If that unit already stored the value of apple, that's what should happen. Okay? Who thinks that that's what will happen? No one? Great. Okay, here's another hypothesis that we had. Maybe the information that this unit stores is look for box G. Okay? So we asked about box G, and you're already in layer 15. Maybe the information is we should output the object that is inside box G, and if that's the case, copy pasting its state should flip the prediction from lamp to peach, right? Because peach was inside box G in the second sentence. So who thinks that what will happen? Great. Okay, great. So we designed this experiment. We have these two sentences that can actually differentiate between these two hypotheses, and then we copy paste the state. But actually, something third was happening, which is the prediction was flipping from lamp to board. Now the question is why board? So it turns out there is another explanation here, which is actually what these units implement is some sort of a pointer to the location of the object we care about. And because apple was the first object presented in the first sentence, now it points to the board, which is the first object in the second sentence. Okay? And roughly speaking, these are the functionality that the model implements in order to solve this task entity tracking, which is, first of all, we have a set of units that actually summarize all the information regarding this sentence. The apple is in box G, and then it actually encode a lot of information regarding the sentence, including the fact that apple was the first object that was presented. And then later on, when we ask about box G, the model knows to basically take that information and transmit the information regarding the location of the word apple downstream. And then at the very end, there is a set of units that actually use the information regarding the location of the word apple, and then refers back to it and knows to transfer it as the final prediction. Okay. What's interesting about this mechanism that the language model implements is we found that many different models actually implement the same mechanism. Okay, so model of different drivers and actually fine-tune models that were fine-tuned on different type of data, they all implement the same mechanism. So it seems like this is a very core algorithm that language models encode. Okay, so we know that entity tracking is being done by tracking the location of entities we care about. Now I want to show you that this is actually also a fundamental a mechanism when we do more complicated tasks like tracking human. So assuming I have a language model, I presented a story with different characters and different observations that they have regarding the reality, how would the model could track these beliefs, especially if they are different from the reality? And this ability to track other beliefs is referred to as a theory of mind. And many people have this ability in a very natural way. There's an ongoing debate whether language models actually have theory of mind ability. So we thought that a very nice way to contribute to that debate is to show that maybe there is an actual mechanism inside the model that is responsible for theory of mind. And let me show you our first attempt to do something like that. So what we did is we presented to the language model a short story with multiple characters. So here's an example for a story like that. We have Noor, she's a barista in a coffee shop, and she wants to make a latte. One of the customers will ask for oatmeal. So she grabs the milk pitcher and fills it with oatmeal. But then a coworker who was not aware of the customer request accidentally swapped the oatmeal with an animal. And Noor was not aware of the swap. And now we asked the language model whether Noor believes that the milk pitcher contains the oatmeal or the animal milk. Now, if the language model has the ability to do theory of mind, it should say that Noor still believes that the milk pitcher contained the oatmeal, right? Because she wasn't aware of the causal. So we found that not only language models are able to answer these questions correctly, but the mechanism that they implement in order to do that is very similar to the entity tracking mechanism I showed you before. Basically, they track the location of the object they care about, whether oatmeal or animal milk, but there is another variable here which basically represents the relationship between the character and the object, kind of like a visibility character, and actually applies in a subspace inside the residual stream of the language model. So language model is not only able to do that, but they can actually encode different information regarding visibility in context. Okay, so we roughly know how language models also track human beliefs. But actually, all these experiments were very, very intensive. Okay? Not only because doing this manual patching technique is very, very intensive, but also because the task of sitting down and hypothesizing regarding possible explanation that units might encode the functionality that they might have, and then designing data that would highlight these explanations is very, very intensive on the researcher side. And this was only for one particular specific task, right? Entity tracking is kind of like a very simple task, and we design it in a very simple manner. We only find 75 attention heads to be part of that. And yet it took us almost a year to find this subnetwork that does entity tracking. What if we want to be able to understand not only one particular task? Maybe we want to understand multiple tasks that the model implements. Actually, maybe we want to understand all possible functionalities that units inside our model encode. And if you want to do that, perhaps you will need to recruit a lot of researchers that will help us conduct all these experiments. And that's actually not feasible with the models of size we see today that contains billions of parameters. This is not only a problem with language models, this is a general problem when you're trying to explain very large AI models. And let me show you what's going on with vision models, okay? So this is how people are trying to explain units inside vision models. Let's assume I have an image classifier, and I'll input this image to the classifier. An image classifier will classify this image as an image of a suit. Now the question is, why will that prediction make? So one assumption is a unit inside the model that does this suit classification, we can find this unit by looking at the neuron that got the highest activation, the highest response for that particular image. And we can also look where in the image the activation was high. Okay, so we can kind of like threshold the activation map and say, okay, the activation was high because this part of the image. Of course, we can't tell anything out of a single image. So a procedure people have suggested is network dissection, and it goes as follows. We take a very large data set, for example, all of ImageNet. We input it to the network and look at the set of images that got the highest activation. Okay? And we call them data set exemplars, and you can see that these kind of serve as a visual explanation of what's going on with that particular unit. So it's nice to have this visual explanation, but it doesn't actually give us precise description of the functionality of the unit. So what we can do is ask people to sit down and label these images. And people will usually come up with a different expression for what's going on with this unit. For example, maybe it's sensitive to genes, neckwear, maybe to male individuals. But again, this is not scalable, right? If you need to collect people to look at these images and label them, we will need to have a lot of people helping us if we want to label all the units inside our classifier. So what people have done is to train an automated method to look at these images and say what they have together or what they have in common. But these methods are often not as accurate. Okay, the reason for that is you can think about it as like one-shot hypothesis generation. They only generate explanation once, but they actually never validate. What we want to do is to be able to scale up the way we explain a unit in a neural network in a way that will be as accurate as the way we interact with the network when we try to explain. Okay, so let's try to write together a sort of a pseudocode for the way we interpret a neural network or a unit inside a neural network. So usually we will do some sort of an experimental loop, right? We will start by formulate some hypotheses regarding the behavior of that unit. And then we will design some test cases that should highlight the hypothesis. And then we will observe the outcome of the experiments and update the hypothesis according to what we saw. And then we can do that, these steps again and again until we reach some sort of a conclusion that we are happy with. So now the question is, how can we automate this? How can we automate this experimental loop to explain the neural network? And what I want to show you today is actually AI models are so powerful, so we can use AI models themselves in order to automate each of these steps. Okay? So let's assume we have a system that we can prompt with a specific question regarding the behavior of our model. And then looking at this question, the system will automatically generate a hypothesis that might explain our question, and then design input that should validate this hypothesis, observe the output, and then update the hypothesis accordingly. Okay? And it could continue doing this loop again and again until reaching a conclusion. And we want this system to be as general as possible in the sense that we want it to be able to interact with any model we care about, no matter what is the underlying architecture, no matter what was the task it was trained on. And we also want it to be able to answer general questions that we might have regarding our model. So this is what we did. We designed an agent. We call it the Automated Interpretability Agent, and I'm going to show you how we trained it. Then I'm going to talk about how we can evaluate explanation that we got from the agent. And then at the very end of the talk, I'm going to show you how we can use the agent not only to explain individual unit in our model, but also to explain global behaviors of the model, and not only explain them, but also to be able to enhance the performance of the model accordingly. Okay, so let's start by talking about how we can actually build such an agent. Okay, so in order to build our agent, the Automated Interpretability Agent, or actually in this case is a multi-modal version of it, so we call it Maya. So in order to build it, we use vision language models. And the reason for that is basically vision language models like GPT-4b, which is our background model, are very good at following instructions. Okay, so we can instruct them with instruction of doing the following experimental loop. We want them to formulate hypothesis, design experiment to test this hypothesis, and then look at the result and refine the hypothesis, and so on and so on. Second of all, they are really good at analyzing textual and visual data. So they can actually look at the results for our experiments and conclude something meaningfully out of it. And third of all, they're really good at writing code. Okay? And this is very important because they can actually write Python code to construct experiments. Okay? Let me show you how we do that in practice. So first of all, we implemented a Python function, a Python library that actually enables the Maya, our agent, to interact with any model we care. Okay? So let's assume that our agent hypothesized that a specific neuron inside a ResNet model is sensitive to airplanes. You can now call that function with an image of an airplane and actually get as an output the activation value that the unit had for that particular image, and also the activation map where in the image the activation was high. And from now on, you will see these two on top of each other. Okay, so the agent can actually autonomously interact with the model to test the response for different inputs, but that's not enough. We also need to get these inputs from somewhere. So for that, we implemented additional Python library with a set of tools. So the first tool is calling these dataset examples, right? Like this set of tools from a large dataset, the set of images from a large dataset that got the highest response from the neuron. We also have additional tools. So the agent can now generate new test cases by calling text to image models. Okay, so it can, for example, generate a new image of an airplane. And it can also edit the images it generated in order to test the causal effect of different aspects of the input image on the behavior of the model. It can also translate images back to text and log everything in an experiment log. And now we have this system. A user can come and ask a specific question. For example, what is the functionality of a specific unit inside our model? And our agent just autonomously starts to conduct experiments by forming a hypothesis, designing experiment, update the hypothesis, and so on and so on. That was a lot of technical details. Let me show you an example for what's going on. Okay, so again, we are looking at the question of what is the functionality of a specific unit inside our model. And usually our agent will just start with calling the dataset exemplars tool, although we never instructed it to do that. But if you think about it, this is a very smart decision because it gives you a prototypical behavior of the unit on a very large dataset of images. So these are the images that got the top activation for that particular unit. And this is where other methods just stop. Okay, you look at this collection of images, try to conclude something out of them. But our agent is interactive, so it can now form multiple hypotheses regarding the functionality of this unit. So here are a few hypotheses like that. It hypothesized that the unit might be sensitive to lower part of faces, or maybe neckwear, in particular bow ties, and maybe it has something to do with formal clothes. And now it starts to design experiment to test each of these hypotheses. So, for example, it starts with testing the bow tie hypothesis. It calls the text-to-image tool with different prompts that it designed in order to generate images of bow ties in different contexts. So we can see many people wearing bow ties on the table without anyone wearing them, and a dog wearing a bow tie. It also uses the image-to-text tool to summarize all these unmasked region back to text. And now it looks at the result of this experiment, as we do, and concludes something out of it. So it sees the result and say, oh, okay, it seems like this neuron is actually sensitive to bow ties. And let's also test more hypotheses. So let's refine the hypothesis now. So the first hypothesis I want to test is whether it's sensitive to bow ties regardless of the context. And then the second one is maybe it's sensitive to bow ties, but only when they are combined with some formal clothing. And then the third one is it wants to also make sure that there's less response to other type of network. Okay, so it has this hypothesis, and now we design experiment to validate them. It started by generating an image of a person without the bow tie. You can see how the activation value of this image is quite low. But then you use the editing tool to add a bow tie to the person. You can see how suddenly the neuron fires. Okay, design more experiments like that. So for example, person wearing a bow tie, place the bow tie really far. You can see how the activation value goes down. A person wearing a hoodie with a bow tie, and then you can place the hoodie with the formal shirt, and you can see how the activation goes slightly up, and so on and so on. The agent looks at this result and concludes that it seems to be indeed the neuron that is sensitive to bow ties, and the sensitivity seems to be a little bit higher when the bow tie is combined with formal clothing. Pretty cool, right? Okay, let's look at a few interesting units that we were able to find with our agents. So now, because this is an automated procedure, we can actually scan our model and find different interesting functionalities in a very large model. So here are a few examples for that. This is an interesting one. This is inside the vision encoder, where we find a specific unit that is sensitive to Spider-Man, but not only visuals of Spider-Man, but also text that has the style of comics. Here are more units. So some units are actually very, very specific, okay? So in the first one here, we can see a clip neuron that is actually very sensitive to the semantic concept of conjunction. So it could actually understand that the word "and" in text, but also the symbol ampersand has the same semantic meaning. Here's another interesting, very specific unit in Dino, which is sensitive to time display. So we can see no matter what was the style of the digits, actually also when there's no digits on the clock, it still fires. Okay, so actually the demonstration I showed you before, by the way, feel free to stop me with questions. You are quite, yes.
Yeah, sorry, I gotta ask a question. Because that's pretty amazing. I mean, you kind of skipped over a little bit. You're like, that's pretty cool, right? And then you like changed it. So that sequence there, you're predefining that, right?
Which sequence?
The sequence of like image to text, text to image.
What we define is the functions that the agent can use. But
Okay.
we don't define the order of them. We actually never show the agent with like the way to compose them together. So the agent knows what the functionality of this data compare tool is, what can it do with like the text to image tool, and so on and so on. But it now autonomously decide how to compose these together into experiments.
Okay, so you give it tools. So you have tool calling, and then so for different images, it's doing like it might do that, and it's always in a chain, right? So you're not imposing like a tree structure or anything.
Right.
Okay, so this one worked, right? When I do this, here's why it doesn't work. Because the agent sees something, and then like it has a hypothesis, it sees conclusion, and then you look at the COT and it's like, oh yeah, like, and it just makes a reasoning error, right? It just like.
Sometimes we see set failure modes like that. I'm actually going to talk about failure modes. Okay. So any specific question about that, or okay?
Well, if you're gonna
Yeah,
talk
maybe
about
we
it,
can. Yeah, maybe we can. Okay. Great. Okay. That was actually a high-level demonstration of how the model works, how the agent works. But actually, in practice, it writes Python code in order to conduct experiments. And I want to show you how the code that it writes actually looks like. And what's nice about looking at the code is it has a really nice documentation. So now we can actually understand why it calls some functions. So again, starting with dataset examples here, these are the images that got the top activations from the dataset. Any guess for what's going on here? What is the sensitivity of this neuron? Okay, usually people will say it has something with round objects, but our agent had actually a more sophisticated explanation, which is it has something to do with spherical objects, but also with hands. Okay, so now you design an experiment to test that. You generate an image of bananas with hands and a cube with a hand, and feed them to the network. They do not activate the neuron match, but then it uses the editing tool to transfer the banana into balls and the cube into a ball. And suddenly the neuron fires, particularly in the area of the ball. So it concludes that this neuron is sensitive to the interaction between hands and spherical objects. Now the question is, how do we know this is true? Okay, this is a unit with a specific behavior, don't have actual description of what it should encode. And this is a general problem with interpretability, right? When you are trying to understand internal behavior, internal mechanism inside a trained AI model, it doesn't come with a ground truth description of what's going on. So something I didn't tell you about this neuron, this is actually a synthetic neuron that we designed in order to have a specific behavior. Specifically, we designed it to be sensitive to balls, but only in the presence of hands in the image. And now, because we have that ground truth description, we can compare it with the explanation from our agent and say whether it's true or not. And in fact, this is part of a more general effort that we are making in order to being able to evaluate explanation from interpretability methods. So in our NeurIPS paper, we designed a very large data set with thousands of synthetic neurons that mimic behaviors of textual neurons that we care about, both from textual domain and from visual domains. And together with an automated evaluation protocol, now we can evaluate the explanation we get from different interpretability methods, including our agent. Okay, so that was about evaluation. Another question that we had regarding evaluation was what are the baselines that we should compare with where we're trying to evaluate explanation from our agent. So because our goal here is to be able to explain the behavior of in units in our network in a way that will be as accurate as researchers in our lab, what we did is we actually recruited researchers from our lab and asked them to answer the same exact question that we asked Maya to solve with the exact same set of tools that Maya has. And now together with the synthetic neurons, we were able to show that explanations that we get from our agent Maya are on par with explanation that we get from the experts, which is great. This is basically what we wanted. But of course, it's not enough to be able to explain synthetic neurons. So what we also did is to evaluate explanation from actual vision models. And from that, we came up with a different protocol. So again, we don't have ground truth description of neurons in vision models. So what we did is we took explanation from for these units, and we kind of evaluated where using this explanation by themselves, we can predict what images are going to make the neuron active and what images are not going to make the neuron active.
What is a synthetic neuron?
So synthetic neuron is a neuron that we built. You mean like technically how we implemented it?
Yeah.
So it depends on the domain, but for visual neurons, we basically took a segmentation algorithm instructed by text, SEM, and we tweaked it a little bit such that it will act as a neuron. So for example, if you want a neuron that will be sensitive to balls, you instructed SEM to segment balls, and now we know where balls in the image are. And we also produced some sort of confidence score, which serves like the activation value in our case. We can actually go into the technical details after the talk. Okay, great. So for actual neurons in vision systems, we have this predictive protocol. We basically try to see if we have only the explanation, if we can predict what images are going to activate the neuron or what images are going to not activate the neuron. And we use various of models, various of neurons from different vision models. And actually using this protocol, over all of them, we were able to show that, again, explanation from our agent are on par with explanation from researchers in the lab, which is amazing. Okay, so I showed you how we built the agent, and I also showed you how we can evaluate explanation from it. And now I want to show you how we can use information that we get from the agent to enhance the performance of the model. And I want to start by actually showing you how we can use Maya in order to explain not only individual neurons inside our model, but the overall global behavior of the model. And in that particular example, I'm going to talk about the task of finding biases in a pre-trained classifier. Okay, so now our agent is not going to interact with neuron inside our model, but instead is going to look at the very final output of the model, the prediction that it makes for a specific image to be belong to a specific class. So in this example, this image got a probability of 76% to be belong to the real class. So now we can ask the agent if there are actually any biases presented in this class from image. Okay? So the agent starts by hypothesizing some possible biases that the classifier might have. The first hypothesis was that there might be some bias towards different social settings. And it writes Python code in order to validate this hypothesis. Let me show you the result of the experiment. So we can see the images that the agent generated and that the probability values that they got. All of them got pretty high probabilities, very higher than 90%. The second hypothesis was that there might be a bias towards unreal context. So you can see the agent generated an image of a real glass on an office desk and a real glass in a sink, and the probability values that these images got. Another hypothesis was something regarding gender bias. We generated an image of a man holding a beer glass and a woman holding a beer glass with the probability values. And another hypothesis was sensitivity to the type of the beer glass. So you can see how we generated different types of beer glasses. So now, conducting the experiment, looking at the results, it concludes that there might be a possibility for a gender bias. And it wants to validate that, so it generated more images to test it. So you can see the images that it generated of men holding a beer glass and women holding a beer glass. And I think at this point, it's quite clear that this classifier actually has a gender bias, right? So Maya was able to see that as well and conclude that there is a gender bias and the classifier tends to prefer men holding a beer glass versus female individuals. And this is very, very important, right? This is an actual image classifier. People are relying on it for downstream applications, but this is actually a bias that no one was aware of before. So not only our agent Maya was able to recover new biases, but the fact that we can now do that in an automated way help us scan a very large classifier. Okay, so now we can look at all the 1,000 classes of an image classifier and look for different biases that it might have. So here are some interesting biases that we found. For example, the Labrador class tends to prefer white for Labrador over other colors. There is also color sensitivity in the suit class, right? So it prefers dark suits over other colors. This is an interesting class. This is the tench fish class. It's the very first class that is included in the ImageNet data set. And if you open the training set, you'll see that it's not actually tench fishes, just like in the wild, but fishermen holding the tench. So this is a very well-known bias that the ImageNet data set has, and Maya was able to recover that bias as well. And sometimes Maya, our agent, will just conduct experiments again and again, and will reach the conclusion that actually there's no bias in that class. So this is what happened here, what's happening here in the flagpole class. And this is actually good, right? We also want to be able that our classifier is actually bias-free. And actually, in fact, in most of the classes that we scanned, we found that there's no bias. Okay, now I want to show you how we can use the ability of Maya to find biases and also to explain individual neurons to actually enhance the performance of a pre-trained model. So for that, we actually trained a classifier with a very particular bias, okay? We used this data set for dog breed classification, But each dog breed is actually sparsely correlated with a specific background. Okay, so for example, corgi will always be presented in a snowy environment. We train our classifier on this data set. But then when we test it on real world scenarios where backgrounds are random, the accuracy that we get is not that good. Okay? And now we want to act as if we don't know what was the training set here. We don't know what is this sparse correlation that we injected to our classifier. We only know that we got this classifier from someone and it doesn't perform that great on real world scenarios that we care about. And we want our agent to help us to solve this problem. What we do is we ask our agent to scan the last layer of our classifier just before it makes the final prediction regarding the dog breed, and to decide whether each of these units in the last layer is actually sensitive to the dog breed or to something else. Okay? Let me show you our experiments like that. So again, the agent started with calling the dataset exemplar tool. You can see that these images cause the top activation for that particular unit. And actually looking at the dataset exemplars, this unit seems to be good, right? Actually seems to be sensitive to one particular dog breed. But actually, along the experiments, Maya was able to show that actually sensitive also to other type of dog breeds, actually respond to them as well, because actually it got something in the background of the image. So this is not a good neuron, and Maya was labeled as a biased neuron. Here's another example. So again, starting with dataset exemplars, you can see how this neuron is sensitive to corgis, specifically in a snowy environment. So Maya generated images of other dogs in a snowy environment. The reaction of the neuron is not that high for other dog breeds. It also tested corgis in different environments, for example, on the beach. And you can see how the neuron is still sensitive to corgis also in different environments. So it concludes that this neuron is actually selective to a very specific type of dog breed. Okay. Now I want to show you how we can use that information. So we actually scan with Maya all the 500 neurons in the last layer of our classifier, and Maya found only 22 neurons out of them to be sensitive to a specific type of dog breed. And again, this is an important point to remind you why scaling up this sort of experimentation is important, right? Doing these sort of experiments manually will take us a lot of time. Okay, so the original classifier trained on biased data, test on actual test cases from real world scenarios, got an accuracy of 73%. But if we use the information that we got from our agent and actually remove all the neurons from the last layer of the classifier, but only keep the 22 that Maya selects to be selective to a specific dog breed, suddenly the performance are much higher. Okay? In fact, the performance are as high as if we just like retrain this last layer of the classifier with a balanced data set of images. So without knowing what is the bias here, and without actually having access to unbiased data, we were able to improve the performance of our classifier by a very meaningful margin. Okay, so our agent is not perfect. It still have some failure modes. One particular type of failure mode that we see is some sort of overfitting. So sometimes it will keep looking for images that will activate our neuron, but we'll only find one that actually caused some response, and we kind of like overfit its explanation to that image particularly. Another type of failure mode that we see is some sort of a confirmation bias. So we come up with a hypothesis. The experiment won't necessarily agree with the hypothesis, but it will kind of like say, oh, I think that my hypothesis is still right. Another type of failure mode that we see are because of the tools themselves. Okay, so for example, in the editing tool, sometimes we'll overdo the edit or we'll underdo the edit. And actually, most of the failure cases that we see are because of the tools, which is actually not that bad, because it means that as the tools that we are using will keep improving, so does the ability of Maya to explain other AI modes. Okay, so that was about Maya. We have a very cool experiment browser where you can see many more results with the full code that Maya produced. And I think the underlying message here is we can actually use AI agents plus AI tools because AI models are so powerful nowadays. So we can use them to actually understand other AI models to a very large scale. Now the question is, what's next? What can we do with it? So I think it's very important to continue to grow our understanding of how AI model operates. And I think we made a very large step towards scaling it to a very large model, but it's actually just the beginning. And there's plenty more challenges if you want to be able to explain models of billions of parameters. One of them is actually when we try to understand models of very large size, the contribution of individual neurons.
I didn't get that. Could you try again?
Okay, that's not a good sign. I hope you'll get that next time. Okay, sorry about that. Okay, so usually with very large models, the contribution of individual neurons is not that meaningful, and actually there's more complex structures that contributes to the prediction of the model. So there is another dimensionality of complexity here, which is what is the right structure to look at. Another challenge is all the models are now becoming multimodals, and we will see probably much more complicated behaviors that are stemming both from, let's say, textual input or visual input, maybe other modalities that we don't even think about these days, but will be part of the next model that we are going to work with. And another challenge is actually state-of-the-art models nowadays. Most of them are black box. So with our agent, our assumption was that we actually have access to the internal representation of the model, but sometimes that's not the case, and we need to also come up with ways to explain black box model or actually interact with them in a way that will give us some meaningful information regarding their internal operation. This is related to a different paper of mine that I didn't have time to cover today, but we should also think about how to explain black box. Also, another challenge is in all our evaluation with the agent, we show that we are kind of like on par with the explanation we get from researchers. But as these models will continue to scale up and will be more and more sophisticated, maybe it won't be enough to have the ability to explain them on a level that is on par with researchers. Maybe we should build agents that can exceed the performance of researchers. This is a very open question. It's unclear how we can do stuff like that today. And actually, we would be able to build these agents that can give us very creative hypotheses and conduct very creative experiments. Maybe we can use them not only to explain systems that are artificial, like our AI models. Maybe we can use them to explain other types of models, for example, maybe neurons in the brain. Okay, so with all these questions, I'm going to conclude and take more questions from the audience.
Amazing talk. I think it's very interesting to show some cases that Maya captures some of the, wrong regions. I'm curious that is it possible like the model will capture some noises and have it not know at the end, and then sort of like do the noise removal. Is it possible so that your sampling is sort of like will remove those information?
Oh, I see. Is the question related to the last application we showed with removing the neuron from the classifier? Yes, so of course this is kind of like a very naive setting that we designed with like the drop-in classification, but hopefully we can scale it up to much more complicated scenarios. I think what's really nice here is that we didn't make any assumption regarding what could be the sparse correlation, but our agent kind of like was able to capture that. So also maybe stuff related to noisy prediction and stuff like that, maybe it will be possible to apply it there as well. Something really nice about this agent is it's kind of modular. right? The way we design it is it can interact with any model of interest, and also the set of tools that it uses they are modular. So if at some point for a specific task like noise removal, you would think that adding an additional tool would be meaningful, you could just add it to the library of tools that it uses, and hopefully on the fly it will manage to use that as well.
Thank you.
So the first step, the first step which you use to explain a particular unit seems to be very computationally expensive. So
Right.
like if you have, you said like 500 neurons, but for models that we care about may have millions of neurons.
Yes,
So how do you choose which neurons to add?
right.
Yeah, and also there's this, you can't expect a single neuron to be specific to something like sparsity argument. So how do you?
Yes. Okay, so for the first question, I think if you have a very particular question regarding a model, for example, when we showed this presentation for one of like the large companies that have like this very common image to text tool that we're all using, they asked me how can we use the agent to make sure that there's no information regarding nudity encoded in the model. So I mentioned that if you have a very specific question regarding the model, you don't really need to do this like very fine-grained experiment for each individual unit, but you can actually do a very rough scan at the beginning and then maybe do a finer scale scan only where you suspect that that kind of information can be stored. So my answer is basically maybe we can do some sort of like course defined scanning instead of like assuming that we are going to scan the full model.
So I'm assuming like you have a large data set of images, like you mentioned it. Now you don't know anything about one particular neuron. So in that case, you'll have to run this whole thing for the whole image.
Yes, so maybe you can start with running with feed forwarding the full image in the data sets and then kind of like get a sense of like where the concept you care about is lying inside the model, and then only then continue to do iterative experimentation. But yeah, you will need to start with like this large data set. And the second question was?
About
Sparsity, yeah. Yeah, actually you see that a lot of neurons are not like monosemantic. A lot of them are polysemantic, and our agent actually, part of our evaluation was to create these synthetic neurons that are polysemantic. Yeah, we started until some level of polysemanticity. Our model, our agent is able to recover multiple concepts. But sometimes if it's very, very polysemantic, it's like more than 10 different concepts, then at some point you'll be like, okay, I'm done. But I found 4, this is enough. But maybe if you introduce some sort of like, if polysemanticity is what you care about, maybe you can introduce some sort of a tree structure for the experiments, saying something like, okay, we already found this concept, can you find something additional for this concept or something?
You're also assuming the text to image or edit image as like an oracle. If those suffer from the same biases, then it's only as good as that.
Right. We definitely see that these tools are kind of like biased themselves. So they definitely have some sort of blind spots. We're trying to, but I think there's a lot of effort to make these tools better. So hopefully we can benefit from that as well. But also, I think currently what we can do is kind of like try to let the agent interact with the tools for a bit to kind of understand, even if we cannot correct the blind spot, just by being aware of the blind spot, I think we could improve the performance. So this is something we are currently working.
Yeah, so thanks for the great talk. So I really like this kind of idea that you have this initial hypothesis, you collect evidence, and you make a decision whether you're gonna refine the hypothesis. Like it sounds like a non-hypothesis testing statistics happening there. So my question is, how the agent would know that this hypothesis is correct or not? And if you adopt this kind of non-hypothesis testing, then how do you draw a conclusion that the non-hypothesis is true?
Right. Right now, it's doing everything, right? It's kind of like hypothesizing, conduct experiment, and then by itself deciding what to stop. That might be not like the best strategy to do that. you can think about like including more statistical skills that like will help it decide where to stop or where like a specific activity was proving in a way that is like statistically meaningful. So right now we don't have it, but this is again because our agent is very modular. I can imagine that we can add these kind of tools.
Thanks.
It seems like there's a couple ways to do evaluation that you talked about. One is you make up your own synthetic problem, and then you show you can recover it. Another one is, have humans look at the outputs, see if they agree. Like you claim you found this thing, let me look at your evidence and see if I agree with sort of a case you've made. And another one is finding these natural occurring things. So the example of the fish, I forget the name, but where the fish is often held by the fishermen.
Yeah.
And that's like a well-known bias in these data sets. We talked about this a little bit before earlier, but there's this question you get whenever you work with LLMs, which is like, maybe it already knows about this thing because it was in the training data.
Right.
So like people have written papers on ImageNet,
Right.
maybe it's sort of it's sort of cheating a bit, informing its hypothesis.
Yes.
My question is not so much like, do you think that's a problem? Because who knows? But like, how would you go about testing?
Yes.
Like, how would you go about trying to assess, okay, how much of this is true, like creative hypothesis generation versus I kind of already know the answer, but I'm going to guess that and check it.
Yeah, great. So I think my answer is going to have two parts. The first part is often in the interpretability community, what we're trying to do is we try to see whether the understanding that we got, like something that we revealed regarding the model, we can actually apply it now in a way that was not included in our training set, if you like. So for example, when I showed like the entity tracking subnetwork in our model, the fact that you can actually ablate all the rest of the units out and you still get the performance of the model means that you actually recovered something really.
Right.
So that's one answer. The second answer is I think we should put some efforts in designing new systems that will be completely unpredictable, that are not relying on factual associations between different, let's say, objects and backgrounds. And this is definitely something we are working on, building these completely random or even counterfactual systems and see whether the agent can also interpret them. It's definitely more challenging.
All right, so let's thank the speaker again.
Is it okay that I ask a question?
Okay. You have access to the tab.
I just logged out, but that is logged in.
Very creative. I think totally similar. How long have I trained it? So you'll go on with the or not mention the research. I'm just glad to know that someone can get it.
No, it's just. So it's just uploaded.
Yeah, it's pretty cool. Also, no stopping condition.
Here, you should have, so we won't be able to see the catalog. You can like, it's sort of like, because I feel like the current evaluation sort of said finally, like, you could already expect the answer. Yeah, there's a possible, like, because some of the domain, have like, the training. And, yeah, sure, it's like, good.
Sorry about that.
Spend,
Yeah,
it's all, I guess, you're said.